So now our guest is, the speaker is Akshay Pai. So Jamuna ma'am from the Department of ISC, Assistant Professor, will introduce the chief guest.
To everyone present here, I would like to welcome Akshay Pai, Team Lead, Data Science. So let me just mention his education. He's educated in BE Engineering from Information Science and Engineering in the year 2011, August to June 2015. So coming to his technical skills, he's well versed in languages such as Python, Java, and frameworks such as TensorFlow, sklearn, PyC, OpenCV, and in cloud, he's well versed in IBM Cloud, Microsoft Azure, Amazon Web Services, and Cloud Platform, virtualization such as Matplotlib, D3. Other skills include Git, Logstash, Alexa, and database skills include MySQL, MongoDB, SQLite, architectures such as microservices and serverless. Looking at his professional experience, currently he's working in Thoughtclan Technologies Private Limited, Bangalore, Karnataka, India. So he's a machine learning engineering and team lead, data science domain. So he has worked under statistical analysis and video streaming processing domains with design, system architecture, and research development in the same field of contextual object analysis. And also he's well versed in working with platforms such as Apache Storm and Apache Kafka. So looking at his next project, he was a team lead for design and implementation of an automated machine learning platform for a Fortune 500 Japanese instrumentation company. So nextly, he's built a no-code platform for training and development of object recognition task with cloud support infrastructure. Then machine learning pipeline for accident detection and vehicle owner recognition. Then he was a team lead in implementation of chatbot builder application. So looking at his previous experience, he's experienced from the company Rare Mile Technologies Private Limited, Bangalore, Karnataka, India. He was working as a software developer in web application division. If you look at the projects, it is image classification system to categorize images of houses and a web application to monitor IoT devices. So he worked here from June 2015 to August 2016. So I heartily welcome Mr. Akshay Pai for the session, and thank you so much.
Hi, good afternoon, everybody, and thanks, Jamuna, for the introduction. And thank you, everybody, for having me here. And it's great to be back and conducting something in terms of machine learning session and things like that. So I think I've just gone through the session, and there are a lot of things that are covered. And I think what we'll be going through today is with something that I've been working on for many years. We'll get into the session, and yeah, a few things is please stop me anytime you want to, if you have any questions that you want to get clarified or if it was not clear, I'll be happy to pause and then we will take it from there. Apart from that, you can also choose to, code along because there are some coding snippets that we'll be trying out, and you can choose to follow along and see the results for yourselves and get some more experience there too. Or if you just want to have a look and understand, that's completely fine as well. We'll have, I think, 2 sessions. One will be today and one will be tomorrow. Today's session will mostly cover on TensorFlow, how exactly it works, and get the concepts of deep learning deep neural networks, basics of it. And with that complete, we will then move to the NLP part. So I think NLP part would be for tomorrow. So that's just the basic gist of how we are going to carry ahead with the session. I hope there are no questions so far. And if none, then we can get started with the session. Okay, so I think Ashivita ma'am, I can get started, right?
Yes, you can start.
Okay. Okay, thanks. I'll just share my screen. Please let me know once my screen is visible.
Yes, it's visible.
Okay, thank you. So I think since Jamuna ma'am has already given an introduction, I'll just go very briefly. So like she said, I have around 6.5 years of experience working as a data science engineer. And from the past 2.5 years, I've been leading the data science team in building all sorts of machine learning platform. TensorFlow is just one of the technologies that we use, but we use other technologies to achieve the same underlying machine learning concepts like image classification, object recognition, and so on. So this is what I've been working on, and TensorFlow, I got an opportunity to work on it since the beginning. That's around 5.5 years ago. So we've been monitoring it, how it changes and so on. So today, what we'll be working on is with respect to understanding what exactly is TensorFlow. So if anyone here has already worked on it, you might know that TensorFlow recently released a very new version called TensorFlow 2.0, which converts TensorFlow from this slightly sophisticated way of developing applications to much simpler, like how other programming languages are built, and it's because it has made it much more efficient, and it has made it much more simple to use. And we'll be covering TensorFlow 2.0. So at its core, TensorFlow is an open source mathematical library because deep neural networks are mathematical concepts, and there are a lot of it entirely runs on mathematical operations, as we're going to see, and how these operations work together. That makes it a neural network, and that's why we need TensorFlow. So it's nothing more than a library that gives us options to implement various sorts of mathematical operations. There are certain differences when you compare TensorFlow with other libraries in Python. So if people who have worked on Python might have come across other libraries, like for example, you might have seen something like NumPys, or you might have seen Python.math, which you might have used. So these are all existing Python libraries, but the way TensorFlow differs from them is that TensorFlow allows you to design the entire neural network and gives you a lot of frameworks and high-level APIs, so you don't have to code every single bits of programming concepts necessary for your neural networks to be ready. So that's one of the reasons, one of the constraints are there, but the constraints is good for us because the neural network that's designed by me or you or anybody else will follow these constraints. It will be like a standard of sorts. Next is, so TensorFlow, Google wanted to put it out such that there's a standard library for running a lot of various scenarios. So based on that, we have TensorFlow that runs on CPUs, GPUs, and also ARM chips. So CPUs are normal PCs. GPUs is where you can actually leverage the power of TensorFlow and deep neural networks, because GPUs are extremely powerful devices that can process a lot of that can perform computations that are extremely high. So we'll be able to get a lot of throughput. And finally, you have ARM chips. These are things like Raspberry Pis. It also has FPGA systems that are also running TensorFlow in it. And what this allows us to do is deploy very simple sort of machine learning applications on the edge. When we say on the edge, we mean that somewhere at the location, like a physical location. For example, it can be like a traffic signal at a on the road, or it might be like a sensor in a manufacturing unit. So that's not in the cloud, that's not in some data center, it's at the site in which it's operating. So TensorFlow runs on these very low footprint devices and also helps us to deploy certain simple applications there. The type of TensorFlow is a base library, but the one which is used to run on these three are slightly different, and it changes in terms of how the installation goes and not the code that you write. So these are the three devices that it would work on. Okay, so moving on. So TensorFlow is a graph flow library. So what it means is that TensorFlow is like helps you build graphs, because in the end, neural networks are like graphs. So you have inputs, you have layers, and then you have outputs. So we'll get into that. But at the core, TensorFlow works based on directed graphs. And what directed graphs, I think what it basically means is that you have the set of tree-like structure which goes from only one direction, either top to bottom or bottom to down. So it's just there's a one single flow and you know which direction it is flowing in. So that's a directed graph. So the basics of TensorFlow has three parts to it. First are the tensors itself. And tensors is nothing but the data that you work with. So that's called as a tensors. And next you have what we call as the nodes. So nodes are nothing but blocks of computational units. So each node on TensorFlow will take some input, it will perform some manipulation and also send some output. So effectively, you can think of tensors as these in terms of networking. These will be some packets and nodes will be routers. So packets will have to pass through the routers where this has some logic in it to manipulate these tensors and send out another tensor. So you can think of it like the nodes will accept tensors and also output tensors after performing some sort of computation. And finally, we have the third component, which is called as the flows. And here flows are nothing but how the tensor should flow. Like if suppose you give a tensor to the network, it should know that it should go to the first node and then the second node, and probably it might skip the third node because of some condition was not met. So the flows will show you that how a tensor can flow. What are the various paths for a tensor to flow from input to the output? So flows represent the graph itself. So in TensorFlow might call it flows, but effectively it's just a graph. So before we move on, any questions on this? Okay. No questions? Okay, we'll proceed. Okay. So this is an example of how a sample flow would look like. Okay, so and basically what this means is that you have a vector. This is the orange one you can see. These are your tensors, and the oval that you see, these are your nodes. And the values, the edges that are going, this is how the flows are indicated. So you can see that these variables are in the form of tensors which go to these particular operations. Now variables in this case, we're just using a constant, which is 15 in this case and 5. And this node is indicating what operation the node is performing. So there's a multiplication happening here, there's an addition happening here, there's a division happening here, and finally you're printing the output. So this is a very simple way of denoting a graph. In the end, a neural network is also a graph, but this isn't a neural network. This is just to show how TensorFlow will represent a graph and identify the three parts, that is the tensors, the operations, as well as the entire flow on how it looks. So let's proceed. So let's look at some of the TensorFlow terminologies. Obviously, because it's a framework and it's to do with machine learning, there are some certain jargons that are used, some certain terminologies that are used. And these terminologies will help you understand the concepts of TensorFlow and as well as what are the components of TensorFlows are. So first thing that we'll be looking at is variables. So variables, like any other programming languages, variables is nothing but parameters that can change. So it can be modified at any point in time, but the only difference that TensorFlow variables has is that most of the time the changeable parameters are separated from the non-changeable parameters. In normal programming terms, we'll call them constants versus variables, but here everything is variables, and underneath that you would be kind of having ways to identify whether there are changeable parameters or not. Next, we have constants. Now, constants are completely separate from variables in the sense that, it does not change like any other programming constant. It doesn't change in the entire duration of the execution. Now, the usage of constants is actually quite low in terms of TensorFlow because almost all the data that we have, it changes some over time. So that's why this is available as a construct, because TF doesn't want to portray as something that will be useful only for building neural networks, but they say that you can use it as a mathematical library as well. So if you want to kind of build certain graphs that perform certain types of mathematical operations where constant is required, you can still use it. Third concept, it's no longer used, but the reason why I wanted to share this is because TensorFlow uses something called as placeholders. Placeholders are just memory values, memory spaces, where you can initialize variables at a later point in time. So what placeholders do is that they just show that this is what type of data it can hold, but it will not hold the data itself. It will just allocate the memory whenever required and whenever used, and then it will be it'll allow us to initialize those variables at that point and then use them. But like I said, these placeholders are no longer used at the moment. There are two concepts which are no longer used, and the reason why I put this is because there might be some people who would have worked on older version of TensorFlow where you might have seen placeholders and sessions being used a lot. And this is one of the changes that has been done with TF2 is that both placeholders and sessions have been, you can say, decommissioned. So what would happen earlier is that you won't be able to directly run something, or you won't be able to directly call a method or perform some operation without first creating a session. So TensorFlow says you design your operations, you design your graphs, and then when you're ready, create a session and run that graph. So everything had to be ready before you could run it, right? But that was not very tedious because there might have been times when you want to compute something and then do other operations, then get some data and then run some more operations. So it was not a very cohesive way to create multiple sessions, manage them and so on. So with TF2, they decided to get rid of session, and instead of placeholders, you can directly use variables wherever you want and change their values as and when you desire. So that was the major change that we are seeing with the current differences between the placeholder, TF1 versus TF2, where these two aren't being used. And all our examples that we will see, you'll be able to see that we are not going to use sessions and placeholders. So people who have been using the TensorFlow earlier, you might find this slightly different, and this is why. Okay, so yeah, I think what we'll do now is I'll just quickly switch to code, and what I would like to show is how a quick concept of what we call as the shapes, right? So basically, whenever you deal with tensors, we have multiple types, like we saw there are constants, variables, and so on. But before we go into TensorFlow itself, I'd like to introduce you to the concept of how an array or a tensor would look like with the help of NumPy, because internally NumPy also follows the same format as what TensorFlow would. Okay. I'm importing this library called NumPy. NumPy is nothing but another mathematical library that helps us define these variables and things like that. So now if you see, for example, now let's say that we create a variable A. And I'll tell that create an as array is what is used to tell NumPy to create an array. And I just give a constant, just a constant variable 5, right? So, sorry, I think I made a mistake. Yeah. So it says that it has created an array, but it's just 5, right? It doesn't have any meaning. And if I see shape tells me what is the shape of the array that I've created. It tells me there is nothing because it's constant. So even if you ask NumPy to create an array which has the shape, which has just a constant value, it doesn't create an actual array. Now let's say we just add these braces to indicate that it's an array of length 1. So now it accepts it, and along with that, it says that you have an array with only one dimension in it. One thing that is different from usual programming language, if you see here, is that we can actually create thing like this, whereas you're saying that it's a 2-dimensional array, but the first, it has only one element in the array within it. Right? And if I just go for the shape, it says that. So here, the way you interpret this is to say that it's a 2-dimensional array because it's showing it in 2 dimensions, where it's a single, it has a single row, and within it, it has only one element within it. So when you talk about shapes, it basically tells you what the shape of the array is, and every tensor is an array. Right? So even if you are passing just 5, there's a very high chance you'll pass it in this form. Or if you, let's say, if it needs to be processed slightly differently, you'll be processing it in a multiple nested level of array. And when you see more practical examples of how it is being used in TensorFlow, you'll be able to relate exactly as to why we are using this sort of a technique. Okay, so I just wanted to give you an example on this. So I think with this, let's move on to the main thing, which is we'll talk first about tensors now. So obviously TensorFlow, everything revolves around tensors. So tensors are nothing but vectors, matrices, and other higher dimensional values. So internally, TensorFlow represents tensors as nothing but n-dimensional arrays. So the reason why I showed the NumPy is to kind of help you understand that how internally TensorFlow maps it. So we on the high level, we may call it vectors, we may call it matrices, or we may call it n-dimensional matrices, or whatever it is. But internally, it just gets converted to some sort of an n-dimensional array, and that's how it uses it. And I think as we saw earlier, there are 3 major types: variables, constants, or placeholders. But placeholders are now replaced directly. I mean, variables have taken up the entire duty of working with instead of placeholders with TensorFlow 2.0. And so now each tensor has basically 2 types of properties, right? One, we call it the data type, which has the values itself. So now what it basically means that if you create a tensor, all the values in it must have the same data type. And this data type, it can be Boolean, it can be integer 32 or a float 32 string, etc. But whatever it is, one tensor should be of the same type. The reason why this is explicitly mentioned is that Python allows you to create multiple types of create an array with multiple data types. Python completely allows that, and you will be able to do it. However, TensorFlow says no, you have to create values which has only, you have to create tensors where the data type is same in all throughout. The second properties of tensor is shape. I think like how we saw the shape of NumPy, the exact same thing is applied here also. So one reason why the shape can be partially known is because what happens is you create an n-dimensional array, but within it you might not know how many elements are present. And that might be decided especially when it comes to neural network. There might be scenarios, or there might be computations or activation functions, what we call it, which can decide whether the tensor shape might change or not change, because it goes through the input from input to output. The shape continuously keeps changing. So we may or may not know. In terms of constants, we will know for sure as to what the shape will be, but variables, it might change. Right? But the data type and the shape will define what the tensor is. Finally, there's another concept called the tensor rank. This tells you what is the dimension of the particular tensor. And it's basically, I mean, in a very simple way, it just gives the number of dimensions there are there. So it is kind of allows us to give us like, an order or the degree at which it is present. So what we'll do is we'll just switch back to our command prompt. And the next set of code snippets that we're going to try out, it's mainly going to be, trying out how these tensor variables work. So let me first start by importing TensorFlow. Take time. So if any of you have installed it, you might face these kind of warnings. Basically, it's saying that it's not able to detect some of the libraries for the GPU. I have installed it and it's not able to pick up the GPU. That's why you get that. But that's warnings which can be safely ignored, which is not a problem. So just it might need a minute to just load. So I'll wait for that. Meantime, if there are any questions you would like to ask, please let me know. Okay, so now it's ready. So what I do is I have some code snippets which I'll just paste here and just explain what's happening. So we have declared a variable called TV shows, and it's initialized by using the tf.variable, which is an internal method to indicate that we are defining a variable. Here you can see that we defined a list of 3 strings, and this tells what variable it is. This is not mandatory, but it is recommended that for readability and maintenance purposes, we tell what sort of variable it is. So effectively, this is telling TensorFlow create a variable of type array which contains string. So yeah, so I mean these are the warnings that come up, no problem. But if we show TV shows, it's going to tell that it first gives you this is what we need to focus on. So if I say TV shows, it says that it's a variable. It has the shape of 3 because it's just like a 3 rows and a single dimension, and then also gives that this is the array that we have. Okay, so I can also create similar fashion, like how we created a string array. I will also create a float array. So just give me a minute. Here, I just created a variable called the famous numbers, which is of the type tf variable same, and it's an array of the value pi and also the other representation of that. So just some examples basically. But here I'm also telling TensorFlow that it's of the type float. So it's a 32-point float value. It can be 64 as well. So similarly, again, if I just try to list what the array is considered, that it's a variable of shape which has 2, nothing. This is none. Null because it has only like a single dimensional array, and it says that this is the value of the array and what is the type. So this is like a summary that TensorFlow gives you on what the tensor is. So this is like a snapshot of the entire tensor. So the famous numbers, the TV shows are all tensors now because we have created it using tf.variable. Okay. So now with this, we'll also be able to kind of try out what we mentioned, right? So it's possible to find out what the rank of that particular, what is the rank of the tensor. So what we can do is you can call simply tf.rank function and tell what you want to give, famous numbers in this case. Okay, and here it says that it's of rank 1, right? So what it means is that there's only one dimension to it. So that's why it says it's 1. So now what we'll do, we'll create another variable which has a higher dimension and then see how the rank changes. So we just call squarish numbers because these are all squares of particular numbers. So that's, and some are not, but many are squares. So we just call it squarish numbers. tf.variable is the basic that we have been using since quite some time to define a variable. Here, if you see that we have a multi-dimensional array because you have a single dimensional array wrapped in a multi-dimensional array, and we're telling that it's of type integer. So now let's call the tf.rank on this. Here you see it says that the rank is of type 2. So here it was 1 because it's a one-dimensional array, and this is 2. So tensors also have these variables of ranks, which we use to kind of identify what is the dimensionality, and the shape will kind of tell us as to what is the actual shape of the tensor. So that's how it's used. So any questions on this? No questions. OK, so just to give, let's dig a little bit deeper into what these tensor ranks are. So obviously you have like the scalar and the vectors. And finally, you have the matrix. Scalar is your constant. Initially with NumPy, when we tested out, we just gave it 5, right? That's scalar, which means it has no array at all. Vector indicates that it's a single dimensional array, and it can be just introduced by introducing a box bracket on each. And matrix is nothing but a higher dimensionality value, which has a 2D shape. So that's 2D, and then 3 tensor and n tensor. So this basically means 3 tensor in the sense that this is the rank is when they say 3 tensor, they're kind of telling you that there's a 3 dimensionality to it. So it's a 3D matrix, for example, will be 3 tensor. And anything beyond 3, it's represented by n tensor. When I say n, let's say if we have a 6-dimensional array, for example, it will be represented by 6 tensor. So this is like more of a terminology on how we kind of use what these tensors are and what is the value of each tensor. So this completes our definitions on what exactly tensors are, how they behave, what is the data type, and how the scalars, how the ranks work. Next, we talk about graphs, right? So data flow graphs allows, first of all, it allows language independent design capability. So what this means is for everybody, I think we saw the example of a graph in the beginning of this presentation, right? So you were easily able to find out what are the various types of graphs that are, how a graph can easily communicate what is happening. So, and representing graphs is not bound to a particular programming language. So if you design a graph, any programming language can see and then start to implement it using its own design philosophy or whatever programming constructs that are present. Secondly, the ability to execute a part of graph on distributed systems. So parallelism is something that is extremely important to machine learning. And the reason is because when you deal with images, when you deal with neural networks, they are very, very, very high computational. We need very high computational systems because there's so many computations. It runs in terms of lakhs of computations that needs to be done. So in order to do that, there needs to be some sort of parallelism that is going by. And if you see any graph, you can very clearly see how you can send one particular value to n different nodes for executing that in parallel. So same way, and that is one of the biggest reasons why it's designed as a graph is because it allows us to achieve parallelism. And not only that, it also allows us to give the distributed execution. The reason between parallel and distributed obviously is the difference. There's a slight difference. Parallel execution is kind of saying that, OK, there is these independent tasks which can be sent across multiple different threads in the same system. And distributed basically means that there are some tasks which will be run on this machine, other independent tasks will be run on other machine, and then we'll collect the data together and then present it. So graphs allow not only parallel, but also distributed, and that becomes another major advantage. And finally, the next thing that we'll talk about is tf.graph. So in the previous code samples, we saw tf.variable, we saw tf.rank. Similarly, we have something called as tf.graph, and this helps us to design the graph or initialize the graph object. So this is the API that we'll use, which will initialize a graph, and then we keep feeding with how the graph should look, what are the various nodes, how the edges should flow, and then finally create the end-to-end graphs for us. So given graphs, all of them come with two properties. One is a structure. So the nodes and edges of the graph, which indicate how individual operations are composed together, OK, but not prescribing how they should be used. So in simple terms, it just defines how the graph should look like, but not what the graph should do. It's like how the placeholder concept is. It just says that give me a data structure that can hold a 3x2 matrix, but don't initialize it any value. So graph structure is something similar, just gives the outline of the graph. And then it has what is called the collections. So connections are in TensorFlow, it provides you a general mechanism for storing groups of related objects, and that is what is collection. So collection can be a set of tensors of the same, like let's say float type, or it can be a tensors of integer type, and it can be of any dimension. And the general term to identify what the data is or how the group of data is, it's called as the collections. Okay, so this is the concept of graphs. So next concept that we will be dealing with is how do we actually build this graph? So we now know that what a TensorFlow graph is and how tensors interact with a graph and how they should be interacting with the graph. So in this step, we'll just be looking at how exactly we will be using this graph and how exactly do we build a particular graph. The first step is we create a node. So like we discussed earlier, a node is nothing but an operation that you perform. That operation can be multiplication, addition, subtraction, or a much more complicated mathematical operation as well. But a node just does some computation at a high level. Once we create a node, the next thing we do is create an edge. So there'll be an edge which will be going into a node. There'll be an edge which is coming out of a node. So that's the next part. Finally, we have to add it. All these nodes and edges that we create, we need to add it to the graph. And how do we do that? It's by using the implicit graph. So because TensorFlow uses graphs for everything, even if you want to multiply two things, it builds a graph. So what it has done is it has given us with what is called as the implicit graph or a default graph. So whenever you try to do something, TensorFlow automatically creates a graph out of that and then uses that graph for execution purposes. So let's just switch back to some coding now to get more understanding on how exactly it would work. Yeah. So let's switch to the command prompt. Yeah. So let's just create two variables here, just to kind of tell you how this would work. Right? So what we have here is two tensors, tensor 1 and tensor 2. Both are of type variable and they belong to the, both are TensorFlow variables with type integer. Here we have a two-dimensional array. And same thing, here we have two-dimensional array, but it has only one element. This has two elements. So you can consider this to be, when you think of a shape of a matrix, right? So this is of the type 1, 2, because it has one row and two columns. And this will be of the type 2, 1, because it has two rows and each row having only one column. So now what we'll do is we'll try to build an operation. So this, according to our builder graph, these are the edges that we have created. So we have two edges, right? Now we need to create a node. So how do we create a node? By creating an operation, because nodes are nothing but operational units. So I will use the function called matmul. What matmul is an internal function provided by TensorFlow, which is basically matrix multiplication. So we take tensor 1 and tensor 2 and we'll ask for the output from it. Thank you. So OP output. So if you see, it has the output is only 26. And the reason why there's only one variable is because if you know the way in which matrix multiplication works, if you have 3 cross 2 and then, for example, if you like, if this is the, sorry, it's 1 cross 2. And when you multiply that with a 2 cross 1, the resultant will be the outermost level. So it'll be 1 cross 1. So that's how matrix multiplication works. So 1 cross 1 is the final resulting value. And that is what we have seen here. There's only one value in it. So effectively what has happened here is that we have created two edges. We have created a node and this node takes in two values and the output edge is stored in OP. So we have total 3 tensors. And when I say implicit graph, the reason why I talked about implicit graph here is because we haven't specifically created a graph here anywhere. All we have done is created an operation and given it 2 tensors and we got an output. Now what we'll do is we'll try to visualize this. We'll show how we can visualize this so that you know how TensorFlow has created this graph and how you can see anything that you do in TensorFlow. How do you visualize it, right? That will be the next step. So one moment, let me switch. Yeah. Yeah, so from what, as of now, let's shift to this, yeah. So the tf.matmul that we have used here belongs to a group of operations called under tf.operation, right? So tf.operation will kind of allow us to run any particular operation on tensors and give an output tensor. So in this case, tensor 1 and tensor 2 input tensors and OP is the output tensor. So yeah, let's any questions here? Or can I proceed to the next part? Hang on. Next, as I mentioned, we will be like, now let's say we have done an operation, we have done a matrix multiplication. And I also told you that there's an implicit graph that has been created. So how can we actually see this graph? And that is going to be the next step. And for that, we use what is called the Tensorboard. Tensorboard is a separate tool which Google provides. It's in the same suite as TensorFlow, but it's a separate application is what it's provided. And what Tensorboard allows us to do is visualize whatever the graphs that is present. So what does TensorFlow provide? Basically, Tensorboard provides a way to visualize graph, to track how well our machine learning model is training, and even to just check what are the different tensors that have been created. All of that can be done from this graph. Okay, so the way this works is we can actually create. One moment, let me just switch. Just give me one moment. Yeah. So what we had, what we'll be doing here is let's create a sample file and create a simple TensorFlow operation, and then we'll see how we will visualize this. Let's call it visualize graph. Okay, so I already have the code ready for it, so I'll just use that and I'll explain as to what exactly is happening there. So this will be very similar to what we have already done. First thing I'm going to do is import flow. Once TensorFlow is imported, the next thing I'm going to do is I'm going to create two tensors like what we had done initially. It'll be pretty much the exact same thing. That is two tensors. Tensor 1 a variable of 1 cross 2, and this will be 2 cross 1. So we have two tensors that we have created. Next, I'll define a function which in the command prompt, what we did is we directly called it here, right, as an OP. So here, what I'm going to do is I'm going to create a function that does that. I'll say tensors. And because we already have the tensors ready, I'm just going to go ahead and create the third tensor, which is output, which equals tf.maximum. Exact same thing as what we did previously, and pass it the two tensors that we have created, tensor 1 and tensor 2. And finally, we'll just say we're going to return the result that comes from it. So now, in order for us to visualize this graph, what TensorFlow does is it creates logs. Like any application, it logs all the things that it's doing. So we have to kind of indicate to it saying that this is a TensorFlow function. So this is called a decorator. And what decorator does is it kind of tells you that this particular method has to be highlighted to the Python interpreter so that it knows that it's a part of TensorFlow. We have some sort of TensorFlow operations is happening. And because of this, we'll be able to capture whatever happens and create logs. And whatever logs gets created, we'll be putting it in this folder so that Tensorboard can then read it. So the next thing that I'm going to do is I'm going to initialize the log directory. So this is a code snippet that I'm going to paste here. Yeah. So let's go through what's happening. So first I've created a log directory, which is nothing but this, saying that under my one of the folders create log directory. And then it provides something called as a summary file writer. So what does this do? So basically summary file writer is effectively telling the system, I can just use here. Yeah. So what it's telling is it needs to create a log file under this particular folder, and whatever logs are generated by creation of these variables and multiplying this and whatever returns as a function should be logged as within this folder, and automatically generate a file, and that file will be read by the Tensorboard for visualization. So here it's returning something, so we'll just call multiply tensors method. It already knows what to use because we have globally defined it. And this is a for summary data to say that log everything. So it's just more like log the graph, and the profiler will log any other metrics that are there. Right? And finally, we call the method that we have created. And then we are saying that once all of this is done, then all the logs that are there under the log directory, that will be under this. So all that it's doing is creating variables, defining how that variable should be manipulated using matrix multiplication. And this will be a standard boilerplate code, which will create a log directory and ask TensorFlow to write the summary of whatever it does into that log directory. So now let's go ahead and run it. So it's going to take a minute to just finish this because it needs to load. OK, done. So there might be a lot of warnings because of incompatibility, but that's completely fine. They're just warnings because TF2 keeps fluctuating very frequently. So now if you just refresh this, if you see, it has written out 2 log files of the events that have occurred by running this particular method. So that what we have done so far is created an operation and written it to logs, right? So now we can run the Tensorboard to see how exactly this function needs to be run. To do that, let me just open another case. If you have installed Tensorboard, you'll be able to just run it by using this command, Tensorboard, and then telling where the log directory is. So my log directory is here. So I'm just going to copy the path and paste it. So I'm just saying run the Tensorboard on this particular log directory. Right. So this will take some time to run, and once it's run, it will open up in a it'll give you a browser window that you can see in the internet browser. So we'll just wait for this to get started. Yeah, so this localhost 5000 is the thing that comes. So if you just go to localhost 6006, it creates, it shows you what is the graph that you have created and all that. So let me just zoom into this for now. Yeah. So if you see, this is nothing but a pure representation of whatever is going on here, right? So we have 2 tensors, we have an operation being performed, and that operation is returned. So if I go back to the Tensorboard, you can see here that you have 2 tensors, which is of type variable, and all the details of this inputs are given. Then your this is like, if you see the previous slide, which tells you need to create edges, you need to create a node, and then this node is nothing but operating on edges to give you the output. So here 2 things are happening. One, 2 tensors are going into matrix multiplication. We are getting the output, and finally we are returning the output. If I switch back here, so if you see here, it's taking in tensor 1 and tensor 2, performing the operation, saving the operation to a tensor and returning that. And that is what is being shown in this graph. Okay. One disadvantage of Tensorboard is that it retains the first graph that it picks up, which means that if you keep running it and keep doing the logs, you'll not be able to see it. So let me just shut this down and delete this, because now I would want to show you another example of how the graph would look like if we added a third variable. So I have the code written and just replace it here. It's the exact same thing as before. Same code, but instead of doing multiplication of just 2 tensors, we are multiplying 2 tensor. We're taking that output and multiplying the third tensor. So it's like a matrix multiplication 3 times of 3 matrices. And the rest of the things are exactly the same. There is no change at all. Just create the summary writer and store it in the log directory. So I will first run this code on visualize graph. So what this should do is it'll create 3 tensors, multiply those 2, and the result should come up here. Yeah, so the logs have been written. I will restart Tensorboard again, and I will go back to this. Now this also will take a minute, so let's just wait for it to run, and then I'll refresh it. Yeah. Now I just refresh this. and we're able to see that the module has changed. So now we have two tensors. The matrix multiplication is performed on that. The output goes to the second unit, and a third tensor that we created goes here. We haven't returned anything, which is why you're not seeing any other output above this. But if we go ahead and return something, that will be created as well. So this is how you'll be able to visualize your graph. And even if you're not visualizing, creating any graph explicitly using tf.graph, TensorFlow will automatically and implicitly create a graph for you, and we'll be able to visualize that graph using Tensorboard. Right? So this covers what Tensorboard does and how you can use it to visualize all your graphs. So any questions here, or can we proceed? No questions? Okay, just a minute. Okay, so this is where we have reached a checkpoint, and excuse me. So this is something that we have already done. So just skip this. That is, we have created two matrices, initialized them with some values. We have created a third matrix and then found the product of those three. We have printed the result as well as visualized the graph. And this checkpoint is exactly what we did here, creating the matrices, performing that, and then for just printing the results, it's as simple as doing a print of the final result. So yeah, that's pretty much it. So now let's go into a brief summary of neural networks and how neural networks work. Okay, so this is, I think this might already been covered. So I mean, it's not going to go very technical or in depth. It's just going to give a very high level overview, because our intention is not to understand deep neural networks in depth, but how we can use simple constructs to build text-based applications, and how do we actually use them. So this is a typical structure of a neural network that you might see a lot of these images online. But the structure on a high level has three parts. You have the input layer, where all the tensors go in terms of TensorFlow. You have the hidden layer, where each of them are nodes. And finally, you have the output layer, which tells you the final result. Now, this is also a node. So three different structures exist here. So the next part is what exactly consists in a hidden layer, right? So we know input is tensors. We know that output also is tensors, but hidden layer is where the entire sort of magic of machine learning happens. It's not really magic, but that's how it appears. But let's look at what exactly happens in a hidden layer. So in a hidden layer, it performs a very simple mathematical operations, and that is represented by this formula here. So what this is saying is that you have a data coming in, which is your input tensor. You're multiplying it by some weight and adding a bias to it. So there are three portions: the data, which comes as an input, the weight, which is added as a part of a particular node, and the bias that gets added. I mean, it gets multiplied by the weight, and a bias is added to it. So the whole purpose of this is to kind of to represent what exactly a hidden layer does. Okay, so activation function is usually a nonlinear function which is applied to every node to kind of help, kind of decide whether it should fire or not. So let me just go back to this. So we see this is a node, right? So it will have something called as an activation function. And what does activation function do? The main reason why it's used is for the neural network to decide whether, based on some data, should it allow the data to pass to the next node, or to pass to all the nodes, or some of the nodes, or none of the nodes. So that is what activation function does here. So it decides whether to fire or not fire. When it fires, it means that it's allowing the thing to pass. When it doesn't fire, or you can say doesn't activate, this particular node doesn't let whatever input to pass, and this signal that is going here gets killed. So there's nothing else going here. So that is what activation function is doing. Okay. So one moment. So now the same thing, we need to see how do we implement this in TensorFlow. Now this might get a little more complex, but you need to just understand it in different parts. So yeah, what happens here is that, okay, what does hidden layer do? So each layer is trying to understand some bit of the entire data. So when you have an n number of hidden layers, it's not saying that everybody knows everything. You're kind of dividing the work. One node is trying to identify. Now let's take a very simple example. Let's say that the machine learning algorithm neural network that you have built is trying to identify if there is if the image that has been given to it is a cat or a dog. So when this happens, image is nothing but a three-dimensional array, which has three channels of R, G, and B. So when a hidden layer encounters it, it doesn't check if it's a cat or a dog. It checks, okay, does it have ears? Then one more thing checks, okay, how does its eyes look? Third checks, okay, what are the structures of the nose? So on. So each hidden layer would have picked up some aspects of the entire image, and that's how they divide the work amongst themselves. So now let's see how one particular hidden layer can be implemented using plain TensorFlow. There's a difference between plain TensorFlow and what we'll actually be doing. But just to understand the inner workings, just this is an example of it. So if you see, firstly, there are a lot of TF operations going. One is add. We have the matmul, which we have tried. And then you're showing that what's the data and the hidden layer bias to it. So effectively, this one statement is creating an operation which represents this. If you see, it's data into weight plus bias, which is what every layer is doing. And that is what is represented here. So you're adding the first component, which one moment. Yeah. So the first component that you have, I mean, in this first, like, the data and the weights part, and then the bias. So and similarly, this is like the first component till here. And the second component, you add in the bias to it. And within the first component, you're multiplying the data that's there, and you're multiplying it with the weight. So that's basically this. The whole thing that it's saying is you're going to represent this particular function of how a hidden layer works in the form of a neural network. So that's what it's doing. Another example is the output layer that we saw can be the nth layer, that is a final layer, will be either a sigmoid or a ReLU in today's terms. So what this is saying is now when data passes through a neural network, it gets a lot of things happens to it. So every node is performing this operation, what is defined here. So when every node performs this operation, the structure keeps on changing and you get a huge long tensor that doesn't mean anything to us. What we want to know is what is the end result. In the terms of classification, we want to know whether it's a cat or a dog, or we would want to know if what type of fruit it is, or we would probably want to know where in the image is the particular house, for example. In order to change the input data that comes to the output variables, the output layer or the last layer uses one of like some construct called a sigmoid. And ReLU is another example of an activation function. But the reason it's saying is that you can either define a layer by plain TensorFlow, or you can use internal methods like sigmoid and ReLU. So when actually building the neural network, we'll go slightly more deeper into what these things are and how they'll be used. Okay. So just a minute. Okay, now what we'll do is next thing is now we know that okay, that it consists of an activation function. It consists of an operation which is performed, and how we can actually achieve it using TensorFlow. These are just examples. But how do we reach the end goal? That is, how do we know if the machine learning or the neural network that we have built is going in the right direction? And if it is going in the right direction, and what else can be done to achieve it? So to do that, we have something called as a cost function. So cost function, it drives the direction of the search for optimal solution. Now, obviously, we're just starting with randomness. It really doesn't know what exactly is looking at, but that needs to be filtered in such a way that it moves to the right solution. The cost function is nothing but helps us to search in which direction should we go so that we get the optimal solution. The most popular way of doing this is called as a gradient descent, which we'll see next as to how is gradient descent actually working. And what the cost function allows us to do is basically help us understand how do we get from the current state of wherever we are to the most optimal state or the goal state. And cost function is helping us to achieve that. The second thing that will help us achieve our goal is the optimizer. An optimizer is nothing but a way in which you can optimize a solution by minimizing the loss. Now, in a concept of ML, loss is kind of identifying how much of good information are you losing. The lesser it is, lesser the value of loss, the higher is the or better the model is performing. So that is how it works. It's inversely proportional. So what optimizer does is it gives us a method to very clearly get to know what our loss is, and it will help us to minimize that loss, that particular loss. So using these two, we'll be able to track how well our model is going. OK, before we move on, any questions here? All right. So yeah. Next thing about the neural network structure. So until now, we saw like what the neural network, each hidden layer does, and we saw how do we do it in TensorFlow and how do we reach the goal or what is needed to reach the goal, right? So now next thing that you'd want to know is how many hidden layers should be there, and in each hidden layer, how many neurons should you add? So that is a question which comes out, right? So the answer is that there are no standards to determine them, and that's true because it's such a wide field that there is nothing that says that you need to have 10 or 100 or 50 or things like that. And it all depends on the use case to use case, which can be found out by trial and error. So there are some rule of thumb that exists, which serves as a starting point, but it's just a starting point, and you'll have to keep experimenting to understand whether it works or not. So yeah, how many hidden layers should you keep? The answer is most cases 1 or 2 is enough. And you'll see now that we'll be building a neural network, a simple one to classify various text elements, like how it will be used in a chatbot. And we'll be using only 1 or 2 neural networks, and we'll also be able to see how well it's able to perform. So it's not like because it's a neural network, it needs very powerful computations, it needs hundreds of layers. Not the case always. There are some places, like let's say in image classification, where there are very complex neural networks, but majority of the simpler cases, only 1 or 2 hidden layers is enough. And the way, just like we mentioned trial and error, here too, we see the test scores, we see the losses. If the losses is still high and it's not performing well, then we can add more hidden layers to say to cover for more sorts of variations. And that's how we'll go in an iterative manner to build a neural network. Finally, how many neurons should be there in each level? So now, again, there is no standards, but what we usually do is we see what the input size is and what the output size is, and you can randomly pick a number between them and see how it performs. If it is not behaving well, you kind of try to change the value and see how it behaves. There are ways in which this particular step is automated, where it quickly changes these parameters and tries to find what is the best combination where the performance matrix are quite high. So those will be done as well. Otherwise, we will just be you can do this manually if you have a fair understanding in the scenario that you are working on. So yeah, as we mentioned, once initialized, varies the size. So basically, we kind of say, OK, let's say the input size is around 75, the output is 5, and we chose somewhere between 5 to 75. Let's say we chose 33. And then we test it. And if the test is not optimal, then we start changing the size to see what size fits value. How does it progress with more neurons and less neurons? And then we'll be able to get the optimal solution. So the entire process of designing, developing a neural network is a trial and error process where you start with some key values and then proceed towards actually implementing it. Okay, so next let's talk about gradient descent. So gradient descent is, like you mentioned, is a cost function that will allow us to identify where we are and helps us to move towards the optimal solution. And the reason why it's called the gradient descent is, I mean, we'll see how that works, but basically, if you try to visualize it, you can see that the value goes from a much higher location to a much lower location, and that's why it's called as the gradient descent. We'll come to that. The second thing is with regard to the output layer. The output layer, like I mentioned, can be sigmoid or softmax and etc. So what are these? So sigmoid and softmax are mathematical operations that take in a huge value that doesn't make any sense and condense them into probability values, which we can interpret. So just to give you an example, let's say that there are values that come across as, let's say we have 50, 20, and 30. So now here the sum of this is 100. So we know that if this is representing the output of, let's say, 3 classes, we know the machine learning algorithm is 50% sure that it belongs to class 1, 20% sure it belongs to class 2, and 30% sure it belongs to class 3. So this is a very easy way to kind of analyze this. So we can easily tell that since class 1 is the highest, we know that the input image which has come to us is very likely belonging to class 1. A more stronger confidence value might be something like it might be 90% sure that it's class 1, and it might be 7% sure that it's class 2, and 3% sure is class 3. This is another way to represent where we know extremely sure that, okay, the probability, it's very high probability that it belongs to class 1. Now to achieve this, we need to apply an output operation like sigmoid or softmax. Sigmoid is usually done when you have a binary classifier, and softmax is applied when you have multiple classes, more than 2 classes as the output. So the point of this is to show that the values don't necessarily come in this format where it's easy to interpret. The values that you might get might be something like 22,331 point something, and it might, the other value might be 291 point something. So it's completely random, right? And the next one, if it's very low, it might be like 153 point something. So when such values come, it's difficult to interpret as to what it's actually saying. And when you run this kind of an input through either sigmoid or through softmax, for example, it might give you this sort of an array through a probabilistic values. Ideally, I've used 100 here, but what it does is it fits between 0 to 1. So if you multiply it by 100, you get the percentage. So that is what the output layer is doing, converting the value that the neural network has worked on, finally giving you a meaningful value to decide on what the output should be. Next, we'll look at how gradient descent works. So there is this animation which is showing. So this is a starting point, and this is the optimal solution. Now, when training happens, you are trying to find out how it reaches the optimal solution in a reasonable amount of time, because sometimes going from here to the optimal solution might take hours, days, weeks, or it might never achieve there because it might get stuck somewhere, because here it looks smooth, but ideally it's not smooth. Every time it is hitting this X mark that you see, it is a kind of like a bump that it encounters. So it doesn't really know whether it hit the bottom or not. For us, when we know the entire data space, we know that, okay, bottom is here. But when the machine is learning, it might not know where the bottom is. So then it has to kind of, and this is an example which shows only in one direction. In scenarios, it will go in all directions, and only the ones which is very strong will then proceed. So that is machine learning, and nothing but identifying what is the best optimal solution. And depending on the use case, some might say that, okay, reaching, let's say the value is 0.5. Let's say if you say that if the Y value is 0.5, I've reached that model is good enough. Some might say, no, I want it to reach the loss to be 0 or 0.1. So based on that, you'll determine when do you stop this process from happening. That's another way. But this is just a simple visualization of how gradient descent is happening. Okay, so now let's just do a recap of what we have seen. So we're seeing that a neural network will have one input layer, which can have n number of tensors. Then it has n hidden layers. In most of our scenarios, it can be one or two hidden layers, where each hidden layer will have a cost function, which will calculate how far you are from the goal, and one optimizer, which will help reducing the loss. And finally, we have the output layer. And after that, the last thing that we do is we have a loss function. Sorry, I mean, this output layer will end the neural network. The loss function and optimizer is going to help us with the achieving all of the entire situation within the hidden layers. So these are how it goes. So the way the progression goes is we design the input layer. We design n hidden layers. So each hidden layer will have a loss function and optimizer. Then we'll design the output layer. And once all of this is done, we run it for n number of epochs. Now, what is this epochs? Once we will be running the neural sample neural network probably tomorrow. But then we'll be able to see what these epochs are and how it will be run. But for now, I would like to show an example of a sample neural network, how it would look if we were to develop it ourselves. So let's get the code, one moment. Now, if we were to actually design a neural network using the base level APIs that we saw, it would look something like this. We would say this is the model where the data is coming, and we would have each hidden layer, which consists of our cost function and an activation function. So that's how it goes. And then finally, we have two hidden layers here. And finally, we have the output layer, which does the same thing. So this is how we would design. But I'm not going to go deep into this because nobody designs neural networks like this. We'll be using very high level APIs to achieve the same. And what these high level APIs are today, I mean, in this thing, we'll be covering something called as Keras, which will help you build neural networks much easier than to actually build every layer using the raw TensorFlow operations that are seen here, right? So yeah, so now let's talk about how do you actually build a neural network with TF. So low-level TensorFlow APIs are nothing but what we just saw. It's saying that it's everything that you're using, tf.add, matmul, etc. are the lowest APIs that you can find for TensorFlow. So this is the way in which if you build a neural network like this, you're saying that you are building it using low-level APIs. But in reality, we don't use that to build. So if that is not done, so how do we do it? So the actual ways in which we do build is by using a high-level API called either TF-learn or Keras. Okay, so what this allows us to do is build much better API it allows us to build neural networks in a much simpler manner, which is easy to read. We don't have to deal with what each layer has, the data weights, multiply variance, none of it. It'll be much simpler, and it's like pre-configured, and we'll just be giving data to it. One moment, let me just check if. No, I think that's somebody who's covers it. Yeah. So this is how it's going to be built. So now before we proceed, we have some NLP concepts which we want to cover. So I think this is what I had in mind for today's session. Tomorrow's session, I wanted to cover some NLP topics and then combine how TensorFlow and NLP can be combined to form a text classifier. So, ma'am, I think we can wrap up here. Or if any, we can open to questions if anybody has any questions and want to get clarified. There are no questions. OK. In that case, ma'am, we can wrap up today's session, and tomorrow we can start with NLP concepts.
Yes, I think I can do that, Akshay. Thank you for an informative session.
Okay, thank you, ma'am. Thank you everybody for attending, and hope it was informative, and we'll continue tomorrow.
Yes,
Thanks.
sir, it's quite informative. But as we should implement all those things, now what you have taught, so then we can have questions. So it was okay. It was nice.
Yes, ma'am. So tomorrow's session. So today's session was just covering TensorFlow. Tomorrow's session is on NLP, and that will get over fairly quickly. And then we will implement the actual solution as to how exactly both will combine. So yeah, we'll be doing that as well. Okay, so can we wrap it up for today?
Yes, Akshay, we can wrap it up for today, and we shall continue tomorrow.
Ma'am, sorry, your voice was very low. Wasn't able to hear anything.
Yeah, I think we can wrap it up for today. We shall continue tomorrow.
Okay, thank you so much. Thank you, everybody. Bye-bye.
Thank you.
Thank you, participants. We shall meet tomorrow morning at 9:30. You can join using the same meeting link.